All right, pressure. Pressure is going to be defined as force per unit area, which has some very strange side effects that aren't really clear. First of all, units wise, again, we talked about this last time. This is newtons per meter squared, and newton per meter squared would be a Pascal. So it's convenient for us to use Pascals whenever we can. Again, Pascals are small units, so we try to do what we can. Sometimes we have to go atmospheres to make our units not ridiculous. The weirdness of pressure is that the area changes the answer. So, for example, a typical person sticking out their arm on planet Earth, as the pressure is pushing down, we would say it is about 15 pounds per square inch, to use an old school unit. If you look at the tops of your arm, you might recognize that you have probably 40, 50 inches on the top. So the amount of pressure applied would be 750 total pounds are placed on the top of your arm at all times. And the good news for you is typically it also pushes on the bottom. This is why suction cups work so well. If you take a suction cup and you push it down onto a surface, if there's 15 pounds per square inch holding it down, if there's no air below it, there's nothing pushing up, so that's a differential of, it could be as much as 30, 40 pounds on a little tiny suction cup, right? So that's why the pressure works that way. The other thing is it leads to all sorts of strange things. Pressure is how people describe lethality. One of the things you used to be able to go, and you can't do anymore because it's cruel to elephants, figure that one out. But we used to take people who apparently didn't make very much money. We used to put boards on their chests. We used to make elephants. Don't make me draw an elephant. I guess I'll have to draw an elephant because you're not even here to see it. So we make an elephant. Oh, that's terrible. I don't even have an elephant here. Let's try legs. Should draw the legs first. Make an elephant. Stick one leg. Whoops, that would be a leg right on top of the head of the poor unfortunate guy, which would be awful. We can't have that. Its head is, that leg is in the background, not stepping on his head. So we have him step on the board, and the person remarkably would survive it just fine. The reason why is there's no penetration anywhere on the board. The board is really large, so the pressure gets spread over a larger area, so he's not crushed. It's the same idea, by the way, it works on beds of nails. If you're on a bed of nails, if you have one nail and you decide to lay on top of one nail, it's going to go right through. It's going to really hurt. Playing a whole bunch of nails makes it possible for you to lay on a bed of nails and survive the experience without even a single puncture. Okay, careful how you get up and down. Other than that, there's enough surface area. The pressure's your own weight. You can survive your own weight. Not a big deal at all. Make sense, sort of? Well, you're not here, so I can't tell. We'll move forward. So problem number 3, go ahead and try problem number 3 and number 4. Hopefully number 4 is correct, although I think there's a glitch with it, so we'll have to do that in a second. But everybody try number 3, and then we'll look at number 4. And do number 4. Hopefully you get a chance to do number 3 and number 4, so let's try number 3. Ball is kicked with a pressure of 10,100 pascals of pressure. The contact area between the foot and the ball is 0.020 meters squared. What's the force applied to the ball? Pressure equals F over A. Therefore, 10,100 equals force I don't know over surface area 0.020. And I get, how did I lose my calculators that fast? The usual part of the class. Here we go. 10,100 times 0.020, and I get 202 newtons of force. Good, no problem. Second one's a little dicier, so let's try that one out. An elephant, and that's a small elephant, 4,500 kilograms. I think that's small. I don't know. Steps on a man with a board strapped to his chest, making the area 0.75 meters squared of area. Okay, so let's try that out. So what's the pressure there? We go pressure equals force per unit area. Pen not working. Force per unit area. Okay, so pressure force per unit area. The pressure would therefore be equal to the force. Now I'm going to say only 1/4 is weight's on there. It's probably a terrible approximation, but we'll deal with it. 9.8 divided by the area, which is now going to be spread over 0.75, right? And so I put that in my calculator, and I get 0.25 times 4,500 times 9.8 divided by 0.75, and chance my answer is correct. I get 14,700 newtons per meter squared, or pascals. Well, I got a different answer there, so that's really good. All right, moving forward, let's try the woman. The woman has got a pressure equals force per unit area. So the pressure be equal to 50 times 9.8 divided by, oh, we should make her half. Let's make her half. And then the area would be, only using the very spike of the high heel shoe, it would be about 0.00010 meters squared. Those of you who doubt that, feel free to go measure the bottom of a spiked heel. Does 9.8 times 0.5 divided by 0.0001, and I get a much larger number than I anticipated getting. Oh, kilopascals. Well, I still didn't get that answer. I think I just did not divide by whatever number I should divide it by. So 1, 2, 3, 4. So I get 240 newtons, 2,450,000 newton meters per squared. So which one's more likely to penetrate your skin? Yeah, that's what I thought. Now, that doesn't mean that it's more likely to crush your ribs. Obviously, the elephant still has more weight coming down on you and could crush your ribs more likely. But the one that's more likely to penetrate your skin and cause great pain and discomfort is the high-heeled shoe. Moving forward, let's talk about the next idea. I'm going to skip lift. We're going to do that later. We'll do that when we're together. Let's talk about hydraulic machines. Hydraulic machines work because they have a cylinder head. And they have a cylinder of some sort with a little tiny hole in the bottom and some sort of tube with fluid in it. Now, it doesn't have to have a little tiny hole. It can have a big one. It can even be a complete thing. But then we have, on this side, we have a smaller piston head. And why is that? How would this work? How would this create the idea? We said before that liquids cannot be compressed. So when I push this down and suck up this much liquid, then this must go not just the same height, it's going to go up much higher because the volume would become larger right there. Right? So these volumes have to be equal because it's not compressible. Okay? Well, what's interesting about that is it changes the force. Two ways to look at that. First of all, we need to remember that if I'm looking at this is pressure equals force per unit area, agreed? Well, the pressure in a fluid is going to be the same throughout. It's going to distribute all the way throughout, not counting depth, which we'll talk about later. Pressure, therefore, is equal to how much force I apply divided by the area which I apply. Which, because this area is smaller, we would say F over A equals F over A. Well, if I increase the area, then I increase the force. So a little tiny cylinder like this, I could push it down and it would have a larger force in the back end. In fact, this is the way we used to operate brakes before we had computers and automatic assist in our brakes. If you push down on a brake on a skinny little tube, it pushes a much larger device with the same pressure, so therefore force per unit area is the same, but a much larger area, so if it's a larger area, much larger force, and you can stop your car by pushing down just a little bit, pushing down on a tube here, creating that situation where it pushes up. The other way to look at it is an old school work equals work. That is force times distance equals force times distance. We just said that the distance is going to be different between these two, right? So therefore, if I increase the distance, I need to decrease the force. So by having a longer distance here, I can use less force to create a greater force here. Both of these equations, by the way, work when talking about hydraulic machines. Okay? So with that in mind, Try number 5 and number 6. That should work. Okay, try those two, and then I'll be right back with you. All right. Dentist chair. I've got a chair that weighs 1,600 newtons. And I've got a rest on a piston with a cross-sectional area. So the area is 1.44 times 10 to the negative third meters squared. Tracked to a little tiny foot pump with a little tiny piston head that would be 7.2 times 10 to the negative sixth meters squared. So how much force would I need to apply on this one to lift it? And second of all, how far do I have to depress this? Which, by the way, back in those days, you would have hit it over and over again. It would have reset and just ratcheted and then repeated. But let's do that. So here we go. We've got F over A equals F over A. So I got 1,600 divided by 1.44 times 10 to the negative third is equal to F over 7.2 times 10 to the negative sixth. So I'm going to cross that out. Exponent negative 6 times 1,600 divided by 1.44, exponent negative 3, and I get a lovely F of 7.78 newtons. Okay? Now if I want to figure out what the distance is, I can do volume equals volume, which would be area times distance equals area times distance, or I can use force times distance equals force times distance. I'm going to use force times distance equals force times distance. So that would be 1,600 times the distance of, when listed 0.1, is equal to the force, which is 7.78, times the distance, solving there. So I go 1,600 times 0.1 divided by the answer from the previous one, and I get the distance would be 20.6 meters. Yes, it took a long time for an old school dentist to get your chair up to where they could actually work on your teeth. All right, good. Let's hope answer number 6 is correct. And then we can talk about buoyancy. So I'm going to skip siphons and pressure depth and density. We will come back to those things, but we got to talk about buoyancy and what makes buoyancy work. Buoyancy happens because when I take a rock or something suitably like it and I drop it in the water level must go up. So this is very similar to when you take a rock and you place it on a scale or a teeter-totter with another object. Okay? If there's an object that's say 10 newtons here and this is 100 newtons, then to hold this up, if I wanted to continue to hold this up, I would only have to use 90 newtons because this thing right here is holding it up with equal amount. I'm assuming equal distance just to make our lives better. Okay? So as I lift that thing up, I lift it up with 90 newtons and the whole thing would hold together, right? If I add more weight here, I have less force over here that I need to lift it with. When I put something in the water, it lifts up the water, which means getting it to go back up, I actually have to reduce the amount of effective weight it has, right? This force that is trying to lift it up, we're going to call it force of buoyancy, okay? And it's dependent on how much water or fluid is being lifted, and specifically how much weight is being lifted. Fair enough? And so as such, what we're going to do here is we're going to go, okay, so how do you calculate the weight of fluid lifted? Okay, well, we know weight is equal to mgh. Therefore, force of buoyancy is going to be equal to m, which is going to be density equals mass over volume. So density of the fluid we're in times the volume that's submerged tells us how much water gets lifted up, and that's going to be equal to mass. And so I go rho v g, whoops, forgot, shouldn't have an h there, right? It's just force of weight. I don't know what I was doing there. I was doing potential energy. So this is my force of buoyancy formula. In other words, how much is submerged is the volume here, submerged. Force is newtons. This is, we know g, this is density. Okay, pausing.